Today we shall deal with the exponential function in the mathematics, the Euler's number E. Believe me, it is playing with the power. Since our school time we have encountered with various constants in mathematics. Pi is one of them. When it is multiplied with the diameter, it offers circumference. And this diameter is twice the radius. So 2 pi r is one interesting formula we have learned with the help of the constant pi, which is 3.14. Under root 2 is another constant that comes from Pythagoras theorem. If you prefer a is equal to 1 and b is also equal to 1, then c is equal to under root of a square plus b square, that is 1 square plus 1 square, that is equal to 2, and this is another constant. I equal to under root of minus 1, it cannot be further solved, and we have designated it a status of imaginary number. Euler's number is another interesting thing which we are going to focus today. What is exponential in mathematics? We shall learn today definition, formula, properties, and rules of exponential function. It is important not only for science students and engineers, but also for a common man, as the interest given on the capital by the banker is calculated from this exponential function, especially the part of continuous compounding on our money deposited. The aggressive growth of coronavirus we have all experienced, which is also exponential in nature, but less understood. The exponential growth is a mathematical concept that describes a rapid and continuous increase of quantity over time. In general, the exponential function f of x equal to a to the power x, which is appearing on your screen, where the input variable x occurs as an exponent and a is termed as base. The exponential curve depends on the exponential function and it depends on the value of x. Today we are going to learn a special exponential function, that is e to the power x. Here the base is e instead of a. This can also be written as exp inside bracket x, that is exponential function. So here on the graph, on the screen you can see a graph where the blue line indicates the behavior of this exponential function that we are going to unfold through this video lecture. Hello friends, you have already started watching my channel. My name is Dr. Shyamkant Anwane. I am professor of physics and working with Science College Nagpur, which is managed by Shivaji Education Society. How the Euler's number E was discovered, which stands for the exponential function, and what is the logarithmic function? There are two types of logarithmic functions. The first one is with base 10 and the another one is with base E, which is also called as natural log. What is the most commonly used logarithm? How do we really understand them? Log to the base E, and the Euler's number E is what I am deeply interested in this discussion. This Euler's number E is also called as magical number. It can also be called as a rational constant, but the brutal truth is that a very few people actually understand what it represents. Log to the base 10 is a kind of intuitive that helps us talk in terms of multiples of 10. Let us see by example. I want to represent a number 1. I can represent it by 10 to the power 0. Anything raised to 0 is 1. If I want to represent 10, it can be represented as 10 to the power 1. 100 can be represented as 10 to the power 2, so on and so forth. So log to the base 10 of x can be represented by these numbers. And Log to the base e is what I am deeply interested in. And if you find log to the base e of x, where this is the range of x, log to the base e of x is 0, or I can say natural log of 10 is 2.302, so on and so forth. Now, let us see how the function behaves. Now, here on the graph, you can observe the log function x, that is log to the base 10. It can be represented by this blue line, and here you can observe that as the number grows to 10,000, it can be represented by 4, where we have seen this in table. Similarly, the natural logarithmic function 10,000 can be represented by 9.21 here on the graph. Let us consider this formula of compound interest that we have learned sometime in our school. A is equal to P inside bracket 1 plus R upon n to the power nt, where P is the principal amount that we are investing. For example, we shall be investing $1 or 1 rupee. Inside bracket we have 1 plus R upon n to the power nt. R is rate of interest. For example, bank is offering 7% rate of interest for the investment. It means that 7 divided by 100, that is 0.07 is the rate of interest. When I am looking for 100% rate of interest, so that the problem of growth by doubling we are considering, then this R will be 100 upon 100, that I can precisely write in decimal as 1.00. Then the next number is n. This is a tricky number. N is the number of times interest is being calculated per year. Now, this is called compounding, and if the bank is compounding every year, at the end of every year, n is equal to 1. If it is 6 monthly assessment, then n is equal to 2. If it is quarterly assessment, then n is equal to 4. Every 3 months we are calculating. If some good bank is offering better rate of interest and better frequency of calculation, compounding every month, so n is equal to 2. Some bank can offer compounding every day, 365 days, n is equal to 365. So n is this frequency. Like the problem of natural growth, I would like to look at this number n, that I should get this calculation every day, rather every hour, rather every minute, second, or microsecond, or even nanosecond. So that leads to the problem of continuous compounding. So this compounding I have to lead to continuous compounding. Then this n number is again appearing here, and t is the time in years. Let us, for simplicity, we can consider t is equal to 1. So for 1 year we are making this calculation, and if you are investing again and again, then this t can be accordingly. So let us take this problem into the zone of mathematical calculations using this formula. Let us try and understand this explanation using the issue of the problem of growth. Say, growth of money in a bank with interest. Let us consider a particular thing. Say a rupee is doubled in every time period. As a matter of interest for anyone, for simplicity of the discussion, we shall consider the time period to be 1 year. And now let us look at this problem in a scientific way. Every unit on x-axis is time, and that corresponds to say 1 year. And every unit on y-axis is rupee, that begins with say 1 rupee at the beginning, and the starting time of our calculation we shall consider t equal to 0. At the end of every year, every time period, the rupee is doubled. Now at the end of first year, you will get 2 rupees. This investment at the end of next year, second year, it will be doubled to 4. And at the end of third year, this will be again doubled to 8 rupees, so on and so forth for the fourth year. It looks as the function is discontinuous. It steps up at the end of every year. Now let us resolve this problem into a natural growth. Say, in a period of 1 year, height of a girl grows by 1 feet, but the growth is not discontinuous. Rather, it is continuous. So you have to account for every day of the year, every minute of the year, every hour of the year, every second of the year, and every microsecond and nanosecond also, to be very precise. So what we shall do, we shall explore this formula where the rate is of doubling, and under this what happens to numbers. Now let us explore this formula. A is equal to P inside bracket 1 plus R by N to the power Nt, and the principal we are selecting from this column, rate of interest is 100% all the time. N is the frequency of compounding, and here we are keeping the frequency of compounding 1 throughout in this particular discussion. And now we are ruling over time. So at the end of first year, the invested amount is doubled, we have seen. Now let us explore the formula. A is equal to principal amount 1 inside bracket 1 plus rate of interest is 1.00. The number of compounding is 1 to the power number of compounding n, which is 1, and we are investing it for 1 year, so 1 into 1. So here you can see this as 2 to the power 1, that leads to this number 2, doubling. Now let us invest this for 2 years. So calculation of A will be 1 rupee invested plus rate of interest is same 100%. This is being invested for 1 year, and to the power 1 into time, this time t is equal to 2, and here it appears. So 2 to the power 2, that leads to 4, so on and so forth. You can pause the video and verify these calculations. At the end of 11 years, 1 rupee will be 2048. Now let us look at the same problem in a very interesting perspective. Principal amount is 1 rupee, rate of interest is 100%, so R is equal to 1 all the time. The frequency of compounding, once a year, 2 times a year means 6 monthly assessment, 4 times a year means quarterly assessment after each 3 months, then monthly assessment, daily assessment, every hour assessment, every second assessment, so on and so forth. You can increase this number magnificently, and let us see how it causes effect on the amount we are going to get at the end of year. So time in year, the time of investment is always 1 year this time. Now the amount we are going to get at the end of year, we have seen it will be 2 rupees, and if we explore the formula, we shall see the return amount A by this formula. Principal is 1 inside bracket 1 plus rate of interest is 1 divided by number of times compounding is done is 1, and this to the power 1. So this leads to 2 to the power 1, that is 2 rupees. but this time n is equal to 2. So A is equal to 1 plus 1 upon our rate of interest is 1 and n is 2, 2 times assessment. So this to the power 2. So 1 plus half, that is 1.5 to the power 2. This leads to 2.25. Actually, what is happening, I'll explain you. We have invested $1 or 1 rupee, and the assessment is with the rate R equal to 1, that is 100%. But we are assessing for 6 months. It means half yearly assessment. So 100% return for half time period. It will be 1.5. And this 1.5 is reinvested with the same rate 1 and for the period of 6 months, that is half year. So 1.5 multiplied by 50% growth. So 50% of 1.5 will be 0.75. So this leads to 2.25. This way we can match the calculation, and here our formula is working. If we are compounding this 4 times, the return will be 2.44. If we are compounding it for 12 times, it will be 2.61. If we are compounding it for n equal to 365, it will be 2.71. Now, if you go on this compounding, go on increasing this compounding frequency, it doesn't lead to infinity. It reaches to a saturation point, or we can see that it converges to 2.718282 for 10 to the power 10 frequency of what you call compounding in a year. So here we are arriving at a problem of calculus where this problem is addressed. A is equal to limit n tends to infinity 1 plus 1 upon n to the power n. So here the answer is 2.718281828845, so on and so forth. This number is called as Euler's number, E, and this is the exponential E. E is the maximum possible result after continuously compounding 100% growth over one time period, that is 1 year. The first result too, here I want to indicate that the first result too is 100% growth without continuous compounding. We are assessing at the end of the year. The second, third, fourth, and so on, after continuous compounding, the growth is 2.71828. This is 171%. That is the maximum growth that we can have. This number exponential 2.718 blah blah blah, irrational number, which means digits after decimal point do not repeat and go on forever. An irrational number is a real number that cannot be expressed as a fraction of two integers. In other words, its decimal representation goes on forever without repeating. But for our convenience, we can consider this up to 3 decimals or 4 decimals. So 2.718 is good for our normal calculations. The question is, what is the role of growth rate and time period? Will this exponential still help us? The growth rate after continuous compounding is given by e to the power rt. So here you can see on y-axis we have f of t equal to e to the power rt, where r represents the rate and t represents the number of time periods. For example, 300% growth in 1.5 years we have to consider. Then it is e to the power 3 into 1.5. So 3 represents 300% growth and 1.5 represents 1.5 year time, amounting this to 90.1. Here you can see. During COVID-19 situations, we were trying to control the nasty growth rate of COVID infection cases by controlling R in terms of social distancing, preventive measures like mask wearing, social distancing, quarantine, and finally the measure was lockdown. So here you can observe that with the growth rate of 1 in 2 years time period, it will lead to 4.48. So e to the power 0 will be 1. So our graph is not starting from origin. Even though x-axis value is 0, y-axis value is 1, and it grows to 4.48 in 2 years with growth rate of 1. With the growth rate of 2 in 2 years, it will lead to 20.08, and with growth rate of 3 in 1.5 year, it leads to 90.01. Now here you can see a table where we have x values which are 1, 10, 100, 1000 and 10,000. It can be nicely represented by 10 power 0. Anything raised to 0 is 1. 10 to the power 1 is 10. 10 to the power 2 is 100. So on and so forth. Now I am fascinated by this number 0, 1, 2, 3 and 4, which actually represents these large values. So logarithmic function is the one wherein we can represent a number like 10,000 by 4. Similarly, natural log x, that is log to the base e of x, which we can write also as ln x, it will be one number will be represented by again 0, 10 will be represented by 2.302, 4.605, and the number 4 can be represented by 9.21. So here log to the base e, where e is 2.7182818, so on and so forth. So for time being we can consider this as 2.718. Now if you try to write e to the power 0, e to the power 1, e to the power 2, 3 and 4, then anything raised to 0, e is replaced by this number, anything raised to 0 is 1, e to the power 1 will be 2.718, e to the power 2 will be 7.389, so on and so forth. So here the number 54.59 can be represented by ln 4. Rather, it is log of 54.59 is 4. On your screen you can see a nice graph where we have horizontal axis as x-axis, and this variable x is called as independent variable. Then vertical axis is y-axis, and the variable y is called as dependent variable, which functionally depends on, say, three functions: y equal to e to the power x, y equal to x and y equal to log of x to the base e. Now let us try and understand this graph precisely. Here, this line y equal to x makes an angle 45 degree with x-axis. So this is for proper aspect ratio of the graph. Now x is rolling from minus infinity to plus infinity. And the first function that we are talking is y equal to e to the power x, x rolling from minus infinity to plus infinity. So when x is equal to minus infinity, we have y equal to e to the power minus infinity. So 1 upon e to the power infinity. So e we have just now calculated, it is 2.718. Now 2.718 to the power very large number will be very small, approaching to 0. So here you can observe that when x is equal to infinity, the value of y function is almost 0. When x is equal to 0, y is equal to e to the power 0, that is equal to 1. So here you can locate x equal to 0, y equal to 1, x equal to 0, y equal to 1, and it is this point. Now as x increases above 0, y also increases in an exponential fashion. This behavior you can observe how rapidly this is growing. Now another function we shall try to understand, and that function, I shall prefer another color, say y is equal to log of x to the base e. Now here this function is defined for x changing from 0 to infinity, and 0 is also not being considered because the function blows at x equal to 0. So when x is very small, when x is close to 0, then y has large negative value. So here you can see when x is equal to 1, log of 1 to the base e is equal to 0. So this is that point. And when x increases above 1, then this log of x to the base e increases. In one of the earlier to the scale plot you have seen this. So here you can see the animation that value of x is coming from minus infinity and it is going to positive value. Y function grows rapidly, that is called as exponential growth, and the logarithmic function y equal to log of x behaves in this fashion. This exponential function has weird properties, and the most important thing about this function is derivative of the function is equal to itself. d dx of e to the power x is e to the power x. A generalized thing I want to tell you that if you are differentiating with respect to x e to the power some function of x, then it is e to the power same function into derivative of the function with respect to x. But I'm considering the clean function e to the power x, its derivative will be e to the power x, and to derivative of x is 1, so the function is same. Now I want to draw a tangent to this curve, and I have to first define at what point I want to draw a tangent, and this tangent will have slope that is given by d dx of this function e to the power x. So at x equal to 0, I want to draw the tangent, so I want to find the slope first. So e to the power 0 will be 1. So the function, which is basically our function f of x, is equal to e to the power x, and I want to evaluate this function at x equal to 0. So f of 0 will be e to the power 0, that is equal to 1, and its derivative is also 1. So function value and its rate of change both are same. This is a very weird property of this function. Now I want to find the slope at this point, x equal to 1. Earlier we have found it for 0. Now we are finding at x equal to 1. So derivative of e to the power x is e to the power x, and at x equal to 1 the value is 2.71828, and the slope is also 21878. So at x equal to 1 we have the value 2.718, and the value of slope of this line is also 2.718. So on and so forth, that will continue. At x equal to 2, the derivative of the function will be equal to itself, and value of the function is 2.718 to the power 2, which amounts to this number, and the value of slope is also the same. So for this green line at this point x equal to 2, we have 7.318. Value as well slope. This is a very weird property of the exponential function. Here, consider the position of a hypothetical rocket that is being represented by function p of t is equal to e to the power t. The position is represented by exponential of time. Now we know that derivative of exponential of time is exponential of time. d dt of e to the power t is equal to t. Second order derivative of e to the power t is also the same. So this leads to a very funny kind of situation where position, velocity, and acceleration all are represented by the same function e to the power t. And at any point of time, position t can be defined. For t equal to 10 seconds, e to the 10 will be 22026. This same number will not only represent position but also velocity and acceleration, but obviously with different units: position in meters, velocity in meter per second, and acceleration in meter per second square. Now this is the actual plot of function e to the power x, where x rolls from, say, -5 to 3. So this nice red line is indicating the exponential behavior in this range. Now look at this integration, e to the power x dx. The derivative of the function is same, so integration of the function is also same. And here we are integrating over limits from -infinity to 0. So we are rolling from say this -5 to 0, or -infinity to 0. The graph is showing from -5. So upper limit minus lower limit e to the power 0 minus e to the power -infinity. So e to the power is 0 is 1, and e to the power minus infinity is 0, and this number is 1. It means that the area represented under the curve from x equal to minus infinity to x equal to 0. I'm trying to shade this area. This area is represented by the integration which you are observing on the screen, and this value 1 indicates the area under the curve. So this nice blue color indicates the area under the curve where x is rolling from minus infinity to 0. Now let us consider the second case, wherein we have integration from minus infinity to 1. This time we are starting from minus infinity. It has 0 y value, and we are going up to x equal to 1. So x equal to minus infinity to x equal to 1, e to the power x dx. This integration is e to the power x. Only the play of limits is from minus infinity to 1. Upper limit e to the power 1 minus lower limit e to the power minus infinity. So e to the power 1 is 2.718 minus 0. It leads to this. Now this will represent the area under the curve from for values x rolling from minus infinity to 1. So I want to shade this area now. So I'm talking about this area. For the range x equal to 1 is the upper limit, and x equal to minus infinity is lower limit. So we're going this way. So this area under the curve is represented by 2.718. Similarly, we shall extend our discussion for the range that rolls from say minus infinity to 2. So the value of x is rolling from minus infinity to 2, integration e to the power x dx, and this leads to the same function e to the power x, only limits are playing from minus infinity to 2, upper limit minus lower limit. So e to the power 2 is 3.7.389. So here I'm talking about the area which is starting from minus infinity. So x is equal to minus infinity to x is equal to 2. So in this region I'm considering this shaded area, and it is extending in the whole region like this. So this the value of area under the curve is 7.389. We are talking about a curve that is being represented by the exponential function and area under that curve. This time I am going to modulate the exponential function that leads to a very interesting gamma function which is very often used in physics. The range of the curve we are considering in the first quadrant where x rolls from 0 to infinity. So these are three nice curves which are being plotted from the function x square e to the power minus x. This is the smallest curve you can observe. The second one is x cube e to the power minus x is this middle curve, and then x to the power 4 into e to the power minus x is the third curve. Now we are interested in finding area under the curve. For this we have to work out integration x to the power n e to the power minus x dx, where x rolls from 0 to infinity. This leads to value n factorial. You can observe here for x square we have area under the curve 2 factorial. Similarly, for x cube we have area under the curve 3 factorial, so on and so forth. Now here we have next function x to the power 0 e to the power minus x. So this curve is being represented by exponential of minus x, and area under the curve is being represented by integration of this function, and the value of this integration appears to be 1, and here we get the proper answer of 0 factorial equal to 1. Now if we show up here a function f is equal to x to the power 1 by 2 into e to the power minus x, then we get a nice curve like this, and integration f of x dx, where x rolls from 0 to infinity for this particular curve, will be able to evaluate 1 by 2 factorial, and 1 by 2 factorial is a very interesting number under root pi by 2. So here we can take a liberty to generalize this integration, where x to the power n e to the power minus x dx, and the limits are from 0 to infinity. This leads to n factorial. This is actually a gamma function, but we shall lead to a popular form wherein the gamma function gamma of n is equal to integration x to the power n minus 1 e to the power minus x dx is equal to n minus 1 factorial. This is one interesting integration using exponential function, often used in physics for many problems. The complex number z is equal to x plus iy, where the meaning of I is equal to under root of minus 1, which cannot be further simplified by Euler's identity, can be represented as r into e to the power I theta, where these variables x and y in Cartesian coordinates can be replaced by the one in polar coordinate being represented by r and theta. The meaning of r is distance of the point xy. This is our real axis, and this one is imaginary axis, and we arrive at the point when we travel x distance along x-axis, real axis, and then y distance parallel to y-axis, leading to the point z equal to x plus iy. Now this point z is at distance r, so by Pythagoras theorem we can write r square is equal to x square plus y square, and locus of all these points is a circle of radius r, and there will be infinitely large number of points on the circle. So to resolve one of them, we need to draw a line that makes an angle theta with x-axis. So by definition, this is called argument, and we can rule theta from 0 to pi. Pi is not permitted, and 0 to minus pi in the opposite direction. Now here we can write theta is equal to tan inverse of y by x. So this makes a complete transformation from Cartesian coordinate to polar coordinate. If you know x and y, you can find r and theta, and if you know r and theta, you can find x and y. So they will be x is equal to r cos theta and y is equal to r sin theta. You have to locate this angle theta, and sin theta is front side upon hypotenuse. So y is equal to r sin theta, and for cosine theta you have to consider adjacent side upon hypotenuse. Now this e to the power I theta is being represented as cos theta plus I times sin theta. When theta is equal to pi, e to the power I pi will be cos pi plus I times sin pi, and cos pi has value -1, sin pi has value 0. So e to the power I pi, which is equal to -1, then e to the power I pi plus 1 equal to 0. This is one interesting relation that comes out of exponential constant, Euler constant E, that comes from exponential function, where we are using I, that is complex number, circular geometry we are using, pi another constant we are using, and this is quite new equation that comes from the definition of exponential. Now here, for the same set of equations, I want to show you a diagram where e to the power I 2 pi is equal to e to the power 0, that leads to anything raised to 0 is 1. So this leads to point here that makes distance unit from origin, and the position vector of that makes an angle 0 or 2 pi with x-axis. In this fashion, we can increase angle, and e to the power I theta, general theta, can be represented here. Another space point at distance r from origin, we can write e to the power I theta, and here in particular e to the power I theta is equal to cos theta plus I times sin theta, and in this particular case theta is pi by 2, so cos of pi by 2 is 0 and sine of pi by 2 is 1. So e to the power I theta is equal to e to the power I pi by 2 is equal to I. So in similar fashion, e to the power I pi equal to e to the power minus I pi. So once we are going this way, second time we are going this way, that is equal to -1, so on and so forth. This Euler's number E can be expressed as series e to the power x, which we can also write as exp of x. This is equal to summation x to the power k upon k factorial, where k rolls from 0 to infinity. So x to the 0 will be 1 upon 0 factorial will be 1. So the first term will be 1. Then x to the power 1 upon 1 factorial will be x square by 2 x square, x cube by 3 factorial will be 3 into 2, that leads to 6. Then x to the power 4 upon 4 factorial will be x to the power 4 upon 24, so on and so forth. Exponential and probability is very interesting thing. We are talking about a winning lottery in 1 million tickets. So probability of winning preferred event upon total number of events, m upon n. So one event is a preferred event over 1 million events. I want to mention here the probability of not occurrence is equal to 1 minus probability of occurrence. So we are using this formula. So probability of losing is equal to 1 minus probability of winning, so that the total probability is conserved to 1, that is 100%. So 1 minus 1 upon 1 million leads to 0.999999, that is the probability of losing is abundant, near to 100%. Now probability of losing every time means it is a problem of composite probability, and you have to multiply all probabilities. So probability of losing every time means 1 minus 1 upon 1 million multiplied by same number 1 million times. This is a problem of calculus where limit n tends to infinity, 1 minus 1 upon n to the power n. This leads to 1 by e, that is exponential. So probability of losing every time is 36%, can be calculated using this exponential function and probability. This is the last one and most interesting example, I believe, which tells weirdness about this exponential function. Let us consider a stick of 10 centimeter, 10 units, that is divided into two parts, identical two parts. 5 centimeter and 5 centimeter, and multiplication of these two numbers, 5 into 5 leads to 25. Then we chop this stick of 10 centimeter into three equal parts, each of 3.33 centimeter. So multiplication of 3.33 three times leads to 36.92. Four pieces chopped identically, 2.5 four times, that leads to 39.06, and further chopping leads to the product 5 times 5, that is 2 to the power 5, 32. So here you can observe that this number is growing from 25 to 36, 36 to 39, and then to 32. What is happening here? The maxima is occurring at 10 by E, and this 2.5 is close to 2.718. That is why this is happening. But to look at this problem in a mathematics sense, we shall go to the next slide. So we shall represent the stick of 10 centimeter divided into number of equal fractions in mathematics and use calculus to handle this problem. F of x is equal to 10 by x to the power x nicely represents this. Now let us try and understand whether this is representing properly or not. We were chopping it into two parts, so 10 divided by 2 to the power 2, that is 5 to the power 2. It is all right. We were having 5 equal parts, x equal to 5, and then the function f is equal to what you call 10 upon 5 to the power 5. So this leads to 2 to the power 5. That is all right. So this function is nicely representing our problem, and the first derivative of this function is appearing on your screen and at maxima. So here this is the point where we are getting maxima. This can be found when the first order derivative is equal to 0, and when we solve this we get x is equal to 10 by e, and when we substitute the value of e we get 3.679, and f of 3.679 is equal to 10 upon 3.679 to the power 3.679. This is equal to 39.59. So here you can observe this point that is appearing here. This exponential function e to the power x has very weird properties. We have seen few of them. The rate of change is always equal to itself, e to the power x. The mathematics marvel has applications in a wide range of areas. Few of them I am able to list, that include signal processing, electromagnetic waves, Fourier transform, quantum mechanics, astronomy, optics, signal analysis, exponential decay in radioactivity, estimation of population growth, mass on a spring, the issue of simple harmonic motion, damped oscillator that also decays exponentially, Newton's law of cooling, all are using exponential function, and the list is unending. Thank you very much for your attention. Comments to open discussion are welcome. Please like and subscribe if you are interested. Thank you very much for your attention once again.